Hello everyone. This is the third part of your lab in the VLSI lab. We have already learned about microwind and BSCH software. In the third part, we'll be using a software called Quartus. I've already supplied you the software. You have to install it. Uh, Now, in this part, we want to teach you about hardware description language. We have all have learned and used programming language such as I think we all have learned Java, be it CSE or EEE students. We all have learned Java. So Java is a programming language. What you do in Java, you write a code, and that code sets a few instructions in the CPU, and it gets executed in the CPU, and it provides you an output. Similarly, in our hardware description language also, we'll write a code and we'll get an output. But the difference between the programming language and hardware description language is that in programming language, the code prepares a set of instructions that will be calculated or that will be performed by the CPU. On the other hand, in hardware description language, it creates a hardware. So this description language actually defines how a specific piece of hardware is going to work. So this is actually more descriptive and more complex than general programming languages. But the biggest advantage that the hardware description language possesses is that if we write a code in the hardware description language, it works in a way that it defines how a specific piece of hardware will work. That is, if we write a code, this language has the capability of transforming that code into an active hardware. We will learn about that thing in a few moments. We'll write a code and we'll see how that code is converted into hardware. That is how that code is converted into a layout diagram. So hardware generally in the code of hardware description language, there are generally mostly used hardware description language are two types: Verilog HDL and VHDL. VHDL. We will use for this course Verilog HDL. So the advantage that hardware description language possesses, especially in case of VLSI, is that we will write a code in if you have a Cadence, that is a software for layout design or the chip IC design. In Cadence, we can just write write a code in Verilog HDL, and it automatically will create the circuit for us. So the digital design entirely depends on our hardware description language. Now, hardware description language is generally of two types. One is structural and second is behavioral. Structural is the type in which we explain or we state the logic gates or the logic blocks that will be used directly, and behavioral is a type of the hardware description language where we state how the circuit will behave. For example, in structural, suppose we want to define a circuit which does the following operation: AB plus C. So if we just state that the circuit will perform this operation, this will go into the behavioral category. And if we say that and it will at first do A and B, then it will do OR C. If we explain it like this, it will go into the structural category. That is, in the structural category, we will specifically mention the different gates or the logic blocks that will be used. But in behavioral code, we will just mention the logic, and all the gates and all the logic blocks will be imported by the software itself. In this lecture, we'll be learning about structural codes. So before we move on to the structural codes, at first let us look at a structure for which we are going to develop a structural code. Let us uh, uh, take this for an example. So this is select, this is A, B. So and here we perform an OR F. Now F is equal to S bar A plus S B. S bar A plus S B. Now this is, if you remember from your digital logic class, this is actually a max, 2 to 1 max. If S is 0, then whatever value is there in A goes to output F, and if S is 1, whatever value is there in B goes to the output F. So this is basically a 2 to 1 marks, and for this marks we have to develop a code that will perform this operation. So before we move on to the code, let us go to the software. The software we'll be using is Quartus. This is the software Quartus that I have already provided you in in Bugs and LMS. So at the interface, you'll see like any other software, there is a menu bar and there is a new and open and all kinds of stuff. So before writing a code in Verilog, there are certain steps which you must do over and over again. These steps start from here, and listen and take notes very carefully. Before you start writing a code, firstly you have to open a project. So we go on File, New Project Wizard. From there, next. Now we have to select a directory for placing that project. So we select the desktop. Suppose in desktop we create a directory called new folder. We are selecting new folder. Here the project will be saved. Now the project will have a name, and this name is very important. For example, we will be designing 2 to 1 marks at first. So we name the project max to 1. Suppose we are naming the project max to 1. The same thing is repeated here. We do not have to write it again. This name is very important, and take a note of this name, and this name will be used in a lot of cases in the future works. Then we press next. We don't have to do anything here. We again press next. Here from the family we have to select Altera. From the family we have to select Flex 10K, and then we can press next. Now the tool name here we have to select custom, and format will be Verilog HDL. Be very careful, not VHDL. We have to select Verilog HDL. Similarly, tool name custom Verilog HDL. Here also tool name custom and Verilog HDL. Next, and we press finish. After we press finish, we have this marks here. This is our project that we have opened. Now we have somewhere where we can write the code. We need that something. So we click new here, and by clicking new here we find Verilog HDL file. We select Verilog HDL file and press OK. And this empty window appears where we can write the actual code. Now, in general, what you if you have learned C language, there is a function called main, and inside that function main, you write the entire code. So here also, in case of marks, you'll be writing functions. You'll be writing a function that will work in that way. The function will have input of A, B, and S, and the function will have an output of F. Now, so the function in case of Verilog is called module. So we write module. Our output is F. Our input is A, B, and S. We have 3 input and 1 output. We place a semicolon after the line is over. Now, this module is function, and this module, like any other function, this module or function requires a name. And this name over here has to be the same as this name, otherwise the code won't work. So we have to write max to 1. Module max to 1, inputs and outputs. Now, in this case, these inputs and outputs we have written in one sort of serial, but there is no serial that needs to be maintained here. But in general, for Verilog, the convention is at first we put the output and then we write the inputs. We write the outputs at first and we write the inputs at last. It is not a problem if we write otherwise, that is, we can write ABSF, no problem with that. But the general convention is we write the output at first. Now, what happens is, in this case, in a 2 to 1 marks, there is only one output and 3 inputs. But there might be some circuits where we have multiple outputs. So we have to define which one of these parameters are output and which one of these parameters are input. So we write input A, B, S and output F. We have written input as A, B, F and output as S. Okay. Now we can see, if we look at the diagram here, we can see we have two AND gates, an OR gate and an OR gate. So let us take any sample AND gates, any sample gate, for example this NOT gate. In this NOT gate, the input of the NOT gate is S, but what is the output of the NOT gate? There is no name given here. So let us give it a name of let us give it a name of Z. So the input of this NOT gate is S and the output of this NOT gate is Z. So we have a NOT gate here. As we say, this NOT is a function of the Verilog itself or the Quartus itself. So this function, as we have already said, that in case of in case of this the Verilog, we at first write the output. The general convention is at first we have to write the output and then we have to write the input. So our output here is Z and our input here is S. So by doing so, if we see this side by side, it would be easier. By doing so, uh, our this gate is covered. Now we are considering this AND gate. If we consider this AND gate, we haven't named anything its output. So we are considering this output as X. If we do that, we have an AND. X is the output and the input are Z and A. Similarly, if we want to write the code for this AND gate, we are considering this as Y. So we have to write this is an AND gate. The input is the output is Y and the input is B, S. And at last we have that OR gate. Of this OR gate, the input are X and Y and the output is F. So we write OR, output is F, input are X and Y. Now one thing is to be noted that this X, Y and Z are random variables that are required in the midway. These are actually wires. So when you write a code so that you want to develop a circuit or something, that is, if you want to build a circuit out of that code, you have to write another line as wire X, Y, Z. Wire X, Y, Z semicolon. This line is required if you want to make a circuit out of this code, but at present we do not plan on making a circuit out of this code. We just want it to simulate. If this line is included, the simulation will not run. So as a result, we comment this line out. So this line should not be included in our code. Now, one thing is to be noted, we have first written the NOT gate, then this AND gate, then this AND gate, then this AND gate. So is this serial necessary? No, this serial is not necessary. That is, you can write these gates in any order. What Verilog HDL does, Verilog HDL takes all the lines and execute all these lines at one go. That is, it does not do it in such a way that it will execute line number 5 first, then 6, then 7, then 8. No. It works in a way that it executes all the lines at a time. So, and another thing is, in this case, do we need to state that Z is the output of this NOT gate and S is the input? Or X is the output of this AND gate and Z and A are inputs? No, we do not need to state that. Because as we have said, in convention, the gates or the functions that are modules that are built in the Verilog, they use these. They use these expressions. They use the convention that output is at beginning and inputs are at last. So we do not need to mention it separately. So this has been done. The code has been done, and since we have started a function here, we have to end the function. So for ending the function, we have to write end module. After the end module, we will not place any semicolon. Any semicolon is not required. So what we do, we first write a function f, a, b, s. that is the outputs and inputs we write, that is the parameters. We define which are the inputs and which is the output, then we define the gates. This is the structural way of coding. Now let us see if it works like a mux. So in order to do that, at first we save the code, Control S, and see, the file name automatically is given mux221, which is this name. So this name should not be changed. If this is changed, the code will not run and there will be errors. So this name is very important. So we are saving this, and after saving this, we use this play button or start compilation and see if there are any errors. Okay. If we have written the code successfully, there will be no errors. There are 6 warnings, and these warnings can be neglected. I'm placing OK. Now this code runs. What does that mean? That means that the syntax of this code is right, but whether the logic is right, whether the output and the input combination that we want is right, that is not proved by this successful compilation. Now we have to check, we have to see whether this is right. In order to do that, we need to see the waveforms of the inputs and outputs. We need to put input waveform and see the output waveform. In order to do that, we click new, we click vector waveform file from here, we click OK, and after clicking OK, this window will appear. Here we'll right click, insert, so right click, insert node or bus. Then we'll go to node finder, and after node finder, we'll see look in mux21 automatically. Since the code was already compiled, this name will automatically come. That is, this step needs to be done once the code has been compiled. So after this, we place list. After list, these things are there, and we have to click this double arrow. So these things that are in the code will come to the waveform, and we select OK, and we select OK again. So A, B, S, these are the inputs, and F is the output. Since no input is given at this moment, the output is X, X, X. That is that this thing denotes that the output is floating. Now, in case of A, suppose let us put A as a clock. So we select right mouse and value. We select clock from here. The shortcut is Ctrl plus Alt plus K. And suppose the clock time period is 10 nanoseconds. And in case of B, we also put a clock, value, clock, and we are doubling the time, 20 nanoseconds, suppose. And in case of S, we are again, will be again doubling the time, that is, we'll be selecting 40 nanoseconds. Why are we considering this is 10 nanoseconds, then this is 20, then this is 40? We're doing that because if we see that we'll get all the logic, all the inputs sequences here. We have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We have all the logics here. In order to get all the logics, all the clocks needs to be twice the previous one. Okay, these clocks have been defined. After these clocks have been defined, we save this vector waveform file. Again, see, the name is mux21. That is the name of the project that we have opened. This is very important. We save this file, and after saving this file, some steps need to be taken. First, we go on to assignments, and first we go on to the assignments and click settings. Then from the settings, here we have simulator settings. Going to the simulator settings, we choose functional. These things must be done after we have saved the vector waveform files. If we haven't saved them, then this thing will not appear and the code will not work. So here we choose functional, we select OK. Then we go on to the processing. After processing, generate functional simulation netlist. If everything is okay, it will be successful. We can neglect the warnings. And then we select this button, start simulation. After we select this button, the simulation will start and the simulation is now successful. When the simulation is successful, let us see if the logic works. This circuit should work in a way that if S is 0, then output is equal to A. If S is 1, then output is equal to B. We can see that in this period of time, S is 0. When S is 0, the output looks same as A. In this period of time, the clock is 1. When the clock is 1, the output looks same as B. So this is working as 2 to 1 max. Now this is a structural way of representing code. That is, we are representing all the logic blocks that will be used. Again, I'm saying the logic blocks are interchangeable, and you can choose logic blocks in any serial, no problem at all. You can choose it in any serial and it will work. And this is a very simple circuit for operation. I'll be uploading the lab sheets with this lecture. In that lab sheet, you'll be finding more complicated circuit, and you can check whether you can you can complete these all the steps, and you can get the correct output out of it. One thing is to be noted that all the steps that I have mentioned, suppose how to open the project and what we need to do from assignments and processing, these steps has to be remembered, and these steps are actually given in the lab sheets that you will be finding. In that lab sheets, everything is written very clearly. If you face any problem, you can visit that lab sheet and you will be able to solve those problems. If you still can't solve those problems, you can contact me by email, or you can contact me via the discussion box of the uh, actual video that I'll be posting in Box, and from there I will be answering to your discussions, and we'll be discussing these things in live classes as well. So far, that's all for this lecture. Thank you so much.